Good morning, anybody watching this at a later point in time. We are getting ready for the test today, so I already read through the announcement in Google Classroom. You guys can pause and read it here as well as far as what we're doing today, but then I also pointed out that we're not having the normal test review because of time. I wanted to focus your attention, and so instead I've gotten you into the practice test. Half of it is going to be the review grade and half of it is going to be for bonus. Some people are still finishing their slope field packet, which is also good review for the test, so I didn't want to pile things on. So you're finishing the slope field extra packet that we've already started. Kids are asking questions on that now, so we're going to keep going on that in just a second. And then as far as review, I do have my work for the first page, and then the other pages, the other questions are AP free response. And so the evens include 2, 4, 6, and then 8. And then there are two different even numbered. This is the question that year that this was on, the free response for the AP test that year. There's 2 evens and 2 odds. So 2 number 5s and 2 number 6s. You guys are doing the number 6s for the test review. Number 5s are bonus. Okay, so then let's get back to the questions they were asking. The questions they were asking on the slope field started off with number 3, which had to do just with the x plus y thing. Andy's question was, how do you solve that with separation of variables? And I was showing if you multiply dx on both sides. I mentioned before, but you guys didn't fully realize because we hadn't practiced a lot, that this is one that we cannot integrate because of that plus. And so they're not asking us to integrate. All they're asking us to do is to use it. So maybe we could use it by plugging in to get a slope of a tangent line, or maybe we could use it by plugging in to find a critical number, or test for a max or a min, or in this case, plug in to get slopes for my baby tangents to make a slope field. But then there was another question just now. Josh has us looking on the, Josh, you said the third page, right?
Yes.
Which one, bud? 15 or 16?
Isn't it 17? 18?
Oh, I was thinking the third side. Sorry, the third page. Got it. Okay, which one do you want me to go to first?
Maybe 17B. I 17 kind of B and down. I don't really know
how to use what you've got. Okay, so quick reminder, and you probably weren't listening because I was doing a recap on the video. But I was mentioning just a second ago when I said how I had told Andy that we can't solve this guy. I was but if the AP were to give this to you, they're asking you to use it somehow. Plugging in points, finding slopes with it, maybe doing some max-min analysis with it. So here in number 17, if anybody wants to pop there in the slope field packet, part A is just graphing. Part A is just plugging in the points and then getting the graph. But part B says write an equation for the tangent line to the curve. Well, tangent line, that's a forever card, right, guys? Isn't tangent line that guy who says y minus y1 equals n times x minus x1? In this case, they give us the point 1, 1. And they give us a place for, not a place so much, but they give us something that we can use for slopes. Remember, the derivative is the slope of the tangent line, right? That's exactly what you do when you make these baby slopes. It's hey, I know the slope, cool. So if you want to make the line, just do y minus y1 equals n times x minus x1. Just do y minus y1 equals n times x minus x1. And so this guy would just be your dy dx. And if you notice on your forever card, I think I've tried to put it here too. For slope fields, n is equal to the differential equation, the dy dx. And so it's a reminder that whenever they're asking me for rate or asking me for slope, I can just use this guy by plugging in. And so I would say dy dx at 1, 1. Which would equal, 1 half. And this is an FRQ. So we can go ahead and say, hey, we've gotten that part done, but just be careful to keep reading the question because then it says to do what?
to estimate the value of 1,2.
Not 1,2. F of x. F of 1.2.
Oh. Yeah.
So what are we doing?
We're supposed to be at the slope. Wait, did the slope change?
Nope. Because you're using the tangent line you just made.
Okay.
Yep, you just take your 1.2 and you just plug it in. And so in our, ooh, what section was that? It was local linear approximation. We were using tangent lines to approximate. It was right at the end of the semester. Last semester or the beginning of this semester. But we figured out that if we get the y by itself, we can say f of some sort of x is approximately the local linearization, which is the same thing as the y. So all I have to do is just add the 1 to the other side and plug in. And technically, you could box it and be done because we can stick it to the man. So we just add the 1, we have the 1/2, but the 1.2 gets plugged in, and that's going to be my approximation. That's back when I was doing the approximates of things like square root of 123 or square root of 79. I was using my tangent lines to try to be snazzy. If you guys remember that. You might not.
Wait, let me see.
Yeah.
But what does it mean by find like the particular solution?
Find the what?
Particular solution.
Oh, that's a different part. What part are you on now?
Let's see.
I was seeing if I had any more of these slope packets that I could use to make an answer key for you guys. Since the slope field guide is due today, I'll go ahead and try to get an answer key posted for you guys this weekend so that you can use it to study like on Sunday afternoon, Sunday night.
I think there is an answer.
Is there an answer key?
I'm pretty sure.
There might be.
At the very end.
Oh, yeah. Okay. Good. I was thinking that there was. But then I knew that I hadn't written it, so I wasn't sure like whether it showed everything, but it does. Sorry, then you're asking for the particular solution, right?
Yeah. And also, like, at the end of part D, I feel like it cuts off.
In part, it's talking about part B, because that's where you found the approximation.
Gotcha.
That we just did. Yeah. Well,
wait, actually,
use your vocab, kiddo, from the whole section, well, the whole chapter 5. Particular solution to a differential equation. Maybe some of your classmates can help you on that too.
Wait, what are the two different types called?
General and particular.
Okay. Is the particular the clue where it gives us coordinates?
But we can't do the clue until we do what?
We separate.
Yeah, we have to actually solve. So remember the third part of our forever card? We're not having a forever quiz because there's only one card. But you should still be peeking at that, right? Solve by, how do we solve a differential equation? We separate the variables. So whether it's particular or general, we solve, we find solutions to differential equations by separating the variables. So what's the very first step?
We're just going to y by itself for x.
Not y by itself. Yeah, we separate our differentials. We separate our dy and our dx. We get them out. Any division of a differential, multiply that up.
So wait, after you separate it, would you get 1 over y dy?
Exactly, because we need to get that y because he doesn't belong, right? So 1 over y dy.
Equals 1/2 x.
And I would just be a lazy bum and pull that 1/2 out, right? X over 2 or 1/2 x dx. This is reviewing, I mean, it's in the slope field packet, but it's the whole chapter 5, because this was 5.3, right? So I'm just going to play for a little bit, and you guys can play, I can play, and we can compare. Sound good?
And then do we find C?
yeah.
But what's your plug into the ports? Since we have like the Y for 1.2.
It gives you the initial condition right here. So we plug in our clue. I mean, we could do it at different points. If Hoban was here, he and I were doing, like, plugging the point in at different times. But you can get your y by itself. This is that special property, again, of exponents where it's e to the x squared over 4 times e to the c. We can make it like a c1 or c2 or c3. It could be a new arbitrary constant.
How come you only put plus C for?
Well, I could have, remember, but then, because this could have had a plus C1, and that could have been a plus C2, and then I could have joined them. So we don't have to show that step every time as soon as we realize, like, what's happening. So we just start shortcutting that process. That would be C1 also.
So will C equal 1 over e to the 4th?
So our particular solution is y equals 1 over e to the 1/4 e to the x squared over 4. Which could be the same thing as e to the x squared over 4 minus 1/4. You could do that.
So it wouldn't cancel out, right?
No, that's an x buddy. They're not even like terms.
Okay.
I can combine and make it x squared minus 1 all over 4 if you really wanted to. Because they have common denominators. But then they say, use this to find, like, this actually is my f of x. Like, I found it. I don't really want to use blue. But when I solve my differential equation, like, I actually found my original function.
And then we plug in for the 1.2.
Mm-hmm.
And is that what we're comparing in D? Because it says compare.
Yeah, because this is the actual 1.2. Like, this is me plugging it into actually knowing what the original was, because this was possible with what we know. The other one was an approximation, so we're just seeing how close they are. Yeah. So I'll put a little dot 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 because they would solve it.
Wait, how come you kept the x squared over e to the x squared over 4? Wouldn't you just put in the? Oh wait, no.
I haven't plugged in yet. Yeah, I found the C, and so I just put them in, and then I was like, that's gross. Like, I can do exponent properties to make it nicer. That's all. Izzy, what are you working on right now, bud?
I guess I'm just saying.
They're showing work. So then if you guys were to check the answer key for part C when they plugged in, oh, okay, they did put it together. Do you guys see their part C? So Josh, like, that's the one way we can write it simpler is the common denominators, but same deal. Let's see if you're getting 1.116.
I think I just messed with my thing because I got like 5 times e to the 10. So I don't think it's.
Oh, that's like a 0. Or e to the 10, that's like 500.
Yeah. Bruh. Sorry.
Double check your exponent. Is all of that up in your exponent?
Oh, I put X instead of 1.
Mm.
And that's probably why I was paying so.
Yeah. And your calculator probably has X as some sort of number. I don't know why.
Yeah, I think X is 10. And so I got 1.116.
Yeah. Right. That's the answer he says.
And then like 18 is pretty similar. So.
All right, everybody. So a question has come in. Another one on the slope field packet, number 18. Another question has come in on the slope field packet, number 18. In an earlier part, before part E, you did already find a particular solution for a different initial condition, but this one is a little bit interesting because it states for a negative number instead of a positive number. So as we tackle this guy, since we haven't done it in here yet, I'm just going to quickly separate the variables, although at this point in the problem you would have already done this. No, not 1 over 1. It's already 1 over. I'm just going to multiply by 1. We could do a plus C. I think Andy was the one that asked last time about that, but I'm going to just realize that I'm moving that plus C over with the other plus C. So I can have that plus C over here. To simplify this just a little bit, I could go ahead and multiply everything by 2, which would give me a new arbitrary constant. And technically I'd have absolute value of y is equal to times 2x squared plus c, the big fat square root. So I think, Josh, what I saw in your work is that you had just seen that in the other problem, the positive square root was what you needed, so that's what you used. But to be technical about it, the absolute value would say plus or minus square root, and then you use whatever is applicable. So for the earlier initial condition, the positive square root was perfect, but for this one, when I plug in negative 1 is equal to plus or minus square root of x squared. Sorry, no, x is 0, right? 0 squared plus c. Even after you like square both sides and you get c is equal to 1, you have to come back up here and you have to realize, okay, even after I plug in that 1, I'm still not going to have this negative unless I choose the negative square root. So my final answer in this one is not the positive square root, or else it would be impossible. My final answer in this one will be negative square root of x squared plus 1.
Does this have to be 1, or could it be like, if we kind of stop right above, like y squared over 2 equals x squared over 2, can we just do it from there?
Well, that would be a version of the c, but remember, like, technically there was like a plus c1 here and a plus c2 here, and this became a plus c3, and then when I put it under a square root, well, I guess it would work even back here though, right? Because yeah, you could have taken it over here. So then you would have had a negative squared as a 1/2 equals a 0 squared.
Or we just have to multiply the 2.
Well, if you had solved for it right here, you would have had this 1/2.
Yeah,
And then that would have needed to come in. And then remember, after that, I did do some math that I wasn't showing, right?
Yeah. Because like when you get under the square root, it'll end up being 1.
The 2 times the 1/2 will be 1, and then the square root will be 1. Yeah, that works.
Okay.
Yeah. But at the end of the day, we did have to choose that negative square root, whereas for the other one, we had to choose the positive square root. That comes back to the absolute value. That comes from the square root of the square. Yeah, go ahead, Andy. And then Lucas, you had a question on, was it the review?
Oh, I figured it out.
Oh, you figured it out? Okay. I'll pause it for now. The question was just kind of clarifying why I had to choose the negative for my particular solution. When you solve for the C early on, you might not realize what needs to happen. When I solve for the C a little bit later, the only way I can have a negative coming out of the square root is if there's a negative right here.
Okay.
So it's kind of like at the end of the day, you need to double check that plugging in actually gets the point that you have. Because if you plugged into a positive square root, you would have gotten out a positive one. You need to plug in and get out a negative one, which will only be possible if I choose the negative square root out of the absolute value.
Thank you. Ms. Diego?
We had another question come in that had to do with section 5.3. Some kiddos that are working on that homework. The tangent to the graph of f at the point xy intersects the x-axis at. Okay, so we know that this point is not in, but on the tangent line. You know, that point is on the tangent line. We could go ahead and make a tangent line equation like y minus f of a is equal to f prime of a times x minus a. We could plug in for our point this one they gave us over here as far as y minus 0 is equal to f prime of actually no, I guess I can't plug it in there. At the point xy. I would technically be plugging this in as another point. So 0 minus, a little bit weird. That's going to be where it's tangent. That's going to be where it's tangent. And then this guy over here is going to be my y with my x. Tangent at the y. F prime of x times x plus 25 minus x. The x's would cancel. And then I could go ahead and say that, let's see, 25 f prime of x is equal to negative y. So f prime of x is equal to negative y over 25. I think they're having us get like a differential equation that we could solve. Yeah, looks to be about like that. Because then what I would do is I would go ahead and rewrite this as dy dx. And I could use my separation of variables to organize all my information the way that I need it to be. So then I would land at dy is is equal to negative 1 over 25. Oh wait, the y goes over here. Yeah, so 1 over y dy is equal to negative 1 over 25 dx. Which would lead me to ln of y. And then this is that thing that hopefully we're getting more and more used to. Taking e would result in y equals c e to the negative 1 over 25x at the end of the day. You see that? And I believe that's what I saw over there too. Yeah. For anybody just joining us, we'll look at number 16 on the slope field packet in case you want to go there, trying to make a match. Remember, as you're looking at your slope fields, you have to think about what you're matching it with. So up until this point, we've been matching, as far as in class, we've been mostly matching with differential equations, like what makes the slope. But what's key for us to realize here is we're not looking at dy dx's, we're looking at y's. And as we look at y's, we don't want to think about the slope. Instead, we want to think about, and maybe that would have been something helpful to put on the card, and I didn't. The dy dx makes the slopes, but the y equals, I put it in the notes. When I think about follow the flow. Earlier in your slope field packet or later, like in number 17 or 18, there's a place where it says pick a point and sketch the solution. The solution flows through. These are possible solutions. Which one follows the flow? If you think about what it looks like, a sine, the flow should look like this around the x-axis, or sorry, y-axis. Cosine should look like this around the y-axis. X squared should look like, as like one representative, x squared would look like, right? X cubed would look like, and ln of x would look like. So the question is, who follows the flow? You see it? Yeah. It's just wrapping your head around what's actually being asked. The y equals says, look at the flow, and the flow in this one is definitely going to be something cubic. Maybe a tangent, like if it was a tangent, that would have been kind of mean, like knowing which one's which. I know. This one would just be a cubic.
So you follow the flow.
Y.
And then how about one? And I know we did example one, right? I was confused.
When it's dy dx, I mean, that would be like another problem in the packet, I think, right? Do you guys have, like these guys? 7 through 10, 11 through 14. I think we already did 11 through 14, or at least some of them, maybe not all of them. So let's look at 7 through 10. These ones you're matching with dy dx's. And remember, these are the dudes that would actually make the slopes. Oh, sorry, wrong. These are the guys that would actually make the slopes. So, let's see, going back. Y equals are the guys who are flowing, and then dy dx are the guys that are actually making. So to keep my color coding accurate. Could have also done something like that. And then the red, let's see. I have something that makes zeros diagonally. So zeros could be kind of at points like, what's it look like? 1, 1, 2, 2, kind of looks like that, 0, 0. So the ends should equal 0 at 1, 1, 2, 2, 0, 0. These ones, the ends all equal 0. at x equals 0. These ones I have zeros at y equals some sort of, I don't even know, maybe y equals 1 or 2. Y equals some sort of constant. These ones I have zeros also at x equals 0, but this also looks like it should be something trigonometric because it's like wavy. See what I mean? So as I go down and as I look at all these different answer options, ooh, I only see one that's trig-y. So I think that this would be with C. Number 7 would be with C. I can always double check if I can actually separate the variables. If I can separate the variables, I can't always, but sometimes I can. You can actually think about who that flow guy would be. A negative cosine looks like a flipped cosine curve. And that's exactly what I'm having. I'm having a flipped cosine curve. So yeah, that one kind of is the only trig one, but also I could anti-derive and think about it, but that's going to be the one that matches that. Andy, do you have any other ideas about who else could match based on me just looking at the zeros? For 8, which one? Any of them. D? Yeah. Because this one's going to have some sort of diagonal, because if I set it equal to 0, it's going to be linear. Y equals mx plus 0. So yeah, he's the only one that would make it go diagonal. And then I have a horizontal one and a vertical one. This guy says if x is 0, this one says if y is 2. And that would, like, I would assume, help you make your last 2 matches. We could also, like, if it starts to be where all of these look so similar, like they're not way different like these ones are, we could also, like, highlight like the first quadrant or something and say, hey, I want the slope to be positive, so I pick like 3, 2 and say it needs to be positive. Who would be positive? I could start picking and choosing like that. If I needed to, I could go by quadrants and look at the ups and the downs and the positives and the negatives, but I think these ones were able to make the matches just by kind of using the behavior.
Wait, was D for 7?
Yeah.
Match it because you just said that's what
You could integrate, but just like this one, you can't integrate. So I'm just saying, like, that is a valid technique to see the upside down cosine, but it's not always necessary. Yeah. And I didn't really just show following the flow, but I could have. The flow would have. Yeah. All right, pausing until we have any other questions. Although we only have about 5 minutes left. So any final questions? Otherwise, I'll start saving the video.